In this next lecture, we're going to discuss unbounded sets, and we'll introduce a notion of a supremum and infimum of such sets. So far, right, we know from the completeness axiom. So completeness axiom implies that every bounded subset or set S, set of real numbers, has both supremum and infimum. Right, because the axiom states that every set bounded from above has a supremum. We proved from the completeness axiom that every set that is bounded from below has infimum, and so therefore every bounded set which is bounded from above and below will have both supremum and infimum. So the question is, what about unbounded sets? And here we're going to basically use a slave hand. We're simply going to introduce the following definitions. Use the definitions. If, so definition number one, if the set S is not bounded from above, then we would say that supremum of S is equal to infinity. Right, so infinity is not a number. What infinity signifies in this case is just that your set is not bounded. So saying supremum is equal to infinity simply means that you're saying that the set is not bounded. Not bounded from above. And then similarly, we can define infimum of a set which is not bounded from below. So that would be the definition number two. If S is not bounded from below, then its infimum is going to be minus infinity. So if S is not bounded from below, then we say that the infimum of S is equal to minus infinity. Okay, so what does that all mean? So in other words, so if we're going to say supremum of S is equal to infinity, this means that S is not bounded from above. Now, what does it mean? The set is not bounded from above. It means that S does not have an upper bound. Right? That's what it means not to be bounded from above. Okay, so if it doesn't have an upper bound, then what does that mean? It means that for any m, let's say it's really for any real m, but we'll say that for any m that is greater than 0, this m is not an upper bound on S, right? Which means what? What does it mean that the number m is not an upper bound on S? That means that for any m which is greater than 0, if a number is not an upper bound, it means that I can find an element of my set which is greater than this number, right? So for any m greater than 0, there exists a number little s in big S such that S is greater than capital M. So conclusion, supremum of S is equal to infinity if for any m greater than 0, there exists an S in capital S such that S is greater than M. Right? So we can take that as a definition of a supremum. And we can do a similar thing with the infimum by making appropriate modifications. Let's see how we can do that. So let's put some labels here. Oops. 1 and 2. Infimum of S is equal to minus infinity. What does it mean? It means that S is not bounded from below now, which means that S does not have a lower bound now. Which says that if I take any m which is negative, then this m is not a lower bound. And if m is not a lower bound, that means for any m like that, I should be able to find an element of my set which is going to be less than m. And so infimum of S is equal to minus infinity. If for any m less than 0, we can find S in S such that S is less than m. All right? Okay, so with that in mind, let's think about what we have. So now choose any set which is a subset of real numbers. Then, what do we know? If S is bounded from above, then supremum of S is some finite real number. Write this as a consequence of a completeness axiom. 1. 2, if S is not bounded from above. Then supremum of S is infinity per what we just discussed. And then we have the symmetric set of statements about the infimum. So we have 3 and 4. Let's put the appropriate modifications here. So 3, if S is bounded from below, then infimum of S is a real number. And 4, if S is not bounded from below, then infimum of S is minus infinity. So what is the conclusion from this? Well, every set is either bounded from above or not bounded from above, bounded from below or not bounded from below. So that means that any set of real numbers is going to have a supremum and infimum. Which both of these numbers can be either a real number or plus or minus infinity. Okay, so let's now discuss some properties of infinite supremum and infimum. And the first thing that I want to demonstrate here or discuss, let's say, suppose now that the supremum of S is equal to minus infinity. What would that signify? Would that be somehow a reasonable thing to have? Well, so this means what? It means that all elements of a set S are going to be below that minus infinity. But that is really not possible, right? Because if the largest element in your set is less than minus infinity, then that's a contradiction, right? So that means that if you have supremum of S equal to minus infinity, we can define what that means as well. It just means that S contains no elements at all, right? Because I cannot have any elements, the largest of which is minus infinity. What does it mean, minus infinity? It's less than any real number. So that's a contradiction in terms. Number 2, if we have that the infimum of S is equal to plus infinity. Once again, what does that mean? That means that every number in the set is larger than infinity, right? Because remember again, that infimum is a greatest lower bound. So that means the greatest lower bound is infinity. Greatest lower bound is greater than any real number. So that is not possible because you cannot have a number which is greater than any real number. So again, this would be a contradiction in terms. So S in that case is also going to be infinity. We will be using these at some point in the future, these conclusions that we're drawing here. Number 3. Let's say I want to show that the supremum of S equal to infinity, where S is going to be a set of all natural numbers, for example. How do I show that the supremum is infinity? What do I need to do? I need to verify one of these conditions, right? Supremum equal to infinity means that no number can be an upper bound. So let's try to verify that. So proof for this. So let's choose any m greater than 0. And what we need to demonstrate is that there exists an element of S which is greater than m. So I'm going to choose any m greater than 0 and consider m and 1. Well, but then by using the Archimedean property, what I will have is that there exists an n in n such that n times 1 is bigger than m, which is the same thing as saying that n is greater than m. So what have I found? The conclusion: there exists n in the set S such that n is bigger than m. So this verifies the definition of a supremum, and so therefore supremum of S is equal to infinity. All right, and in the next lecture we're going to do a couple more examples of this, and we also prove one important theorem about infinite suprema of sets.